Hello everyone, my name is Han. I'm a PhD candidate from University of Toronto Institute for Aerospace Studies. The topic that we bring today is about the strategies of defending a target against multiple intruders. We all know that the market of UAVs has been well developed, and there are lots of off-the-shelf products that everyone can buy these days. So you can basically fly a drone around and taking pictures and delivering good and do whatever you want. This seems very good, but it also brings a lot of concerns. For example, sometimes you just do not want to see any drones in some prohibited areas, like near the government buildings or near the airport. So in those situations, what you hope to do is to keep those drones out. Like in order to ensure the safety, we need to use the worst case assumption that the intruding drones also try to optimize their strategies. And this assumption will actually give rise to a differential game formulation. Well, in the game, each player has its own goal to achieve. For example, in this one, the goal of the intruder is to get as close as possible to target, better enter it. But on the contrary, the goal of the defender is to keep all of the intruders, actually the minimum distance of all the intruders to target as far away as possible. Because the intruders are intelligent, capable of optimizing their strategies, when we designing the defending strategy, we should take that into consideration. So here in this presentation, we're going to design the intruder strategy first. Well, since the intruder wants to get inside the target and avoid capture, intuitively, the first question for them to ask is, what are the safe places to go? Well, to answer this question is very straightforward. You basically can pick up any point in the plane and compute the time it takes for each player to reach that point. And for each individual intruder, the points that takes it less time than the defender to reach makes up an area called the dominant region, and that area is convex. So apparently inside this dominant region, there exists a single point called P star that is closest to the target. And this point is actually the best choice, best direction for the intruder to go. And actually, this point is also the best choice for the defender. So this strategy is called DRX, and it's optimal solution for the single defender, single intruder game. And the DR stands for the dominant region, and X means it only requires location measurement. Well, but the DRX strategy is only optimal for the intruder when the defender is also playing DRX. So the question is, what if the defender doesn't? Well, so the solution for this question is pretty similar to the previous slide. Here we can assume that instead of going to the optimal direction, the defender takes some time to reach another point, D prime first. Then we can ask the same question, what are the safe places for the intruder to go? But under the condition that the defender will, take some extra time, delta t, to move to D prime first. Well, that will give rise to the augmented dominant region, which is still an convex area, but a little bit larger than the original dominant region. And similarly, there also exists a point called augmented P star for the intruder to go. So, and that will give the optimal strategy under this case. And we call it DRV, and V is because we need to measure the defender's velocity for this case. And there are two versions for DRV. The first is when the defender can only know the current velocity of the defender. And that will be a greedy strategy, and we have to take delta t very close to 0. And in other situations is when the intruder can predict that the defender will move along that direction for a period of time. And in that case, we can take delta t as a positive value, and this strategy is labeled as P for prediction. Well, so that's the end of the intruding strategy. So here we're going to design our defending strategy on top of that. So defending strategy we use will be the greedy strategy of an approximated value function. Well, the value function is a term of differential games theory. We don't have time to explain it, but it's It's just like a cost function, but it has a very good property that its gradient strategy is also optimal. But the value function is pretty hard to solve. So in this work, we're going to use some approximation for the value function. We actually are going to talk about two approximations, each on different assumptions on the intruder's knowledge about the capture order. And we're also going to present a very intuitive strategy to compare to those gradient strategies. And this is called minimum dominant region, which means the defender will first capture the intruder with P star closest to target. Okay, so let's talk about the first approximation first for the value function. This is under the assumption that the intruder know the complete capture order. Well, under this case, apparently the first intruder will use DRX because it's optimal. But all of the rest of the intruders will use DRVP under the assumption that the defender will spend some time to capture all the intruders before it one by one. So use this reasoning, the defender can predict the best capture order and compute the closest distance the intruder can get to the target. And that value, that closest distance, is the value for our Vn value function. And the corresponding defending strategy is called VnVg, meaning the gradient strategy of this Vn value function. And the second V means it requires to measure the velocity of the intruder. The computation for our second approximated value function is very similar, except that all the untargeted intruders will treat themselves as the next to be captured. So under this reasoning, using a very similar approach, or we can compute V1 and the corresponding strategy is called V1VG. So yeah, that's all of our strategy design. Now we are going to compare the performance of the three proposed defending strategies and three proposed intruding strategies. So here we do the intruding strategy first. We fix the initial locations of three intruders and change the initial location of a defender. And for each simulation, we run the game with different intruding strategy. And in this set of simulation, we compute the closest distance to target that the intruder, the middle intruder, can get. And shown in this figure is the difference between using DRX and DRVP. So in this figure, the larger the value is, the better DRVP is compared with DRX. So we can see that DRVP, well, it doesn't outperform DRX all the time, but in originally half of the regions. And also in the areas that DRVP win over DRX, the margin of winning is much larger than where the DRX win. So in general, DRX is less good as DRVP. So if we do the similar thing to DRVG, we'll have the similar result, but DRVG is a little bit less good than DRVP. So the complete order of these three strategies is DRVP better than DRVG and then DRX. So because DRVP take the most use of the velocity information of the defender. So this actually tells us the better the intruder use the velocity measurement of the defender, the better it can do. Okay, so this is about the intruding strategy. For defending strategy, we do the similar thing. It's just here, this time we will compute the closest distance to a target among all the intruders. And the three figures are for main DR, VnVG, and V1VG. So we can see that the gradient strategies are better than main DR in general, but V1VG plays better than VnVG because in those corner areas, VnVG is too conservative. The defender thinks the intruder can get inside the targets anyway, so it will take a random action. So we can see that the better assumption the intruder knows about the intruder, the better it can do. So yeah, that's all about our work. Thank you very much.